All right, so this is section 16.2a, video number 3. We're definitely going to just push through all the rest of the examples in this video so I don't have to post a fourth one unless something happens to my computer and I have to do something weird, but I'm planning on pushing through. All right, so we want to find the line integral of xy plus natural log of x dy. So that's a little bit different. We haven't seen that before. So I'm just going to make a note here that we're actually going to talk about the meaning of this on the next video. So on part B, we'll talk about the meaning of it. So instead of ds, it's going to be dy. So it's going to be treated a little bit differently. As far as doing it, won't be that hard to do. All right, so let's see what we've got. We want to find the line integral where c is the arc of the parabola y equals x squared from 1, 1 to 3, 9. Now you could go ahead and sketch that if you want to, but I'm not going to worry about sketching what it looks like. So the basic idea here is that y equals x squared is our function. We are going to need to parameterize it. This is a relatively simple one. Seems like the trivial parameterization would be the easiest. So we'll just say that x equals t, and that makes y t squared. So what are we going to go from here? Well, we're going from, let's see, if x is 1, t is 1. If x is 3, t is 3. So we're going from 1 to 3. T is going to go from 1 to 3. You could have done the same thing with y. If you plug in 1 for y, t would be 1. If you plug in 9 for y, t would be 3. So either way, it's going to be 1 to 3. The important thing is here, we are going to need this dy portion. So dy, let's find it. That's just the derivative of y with respect to t. So dy is going to be 2t dt. You could have written it as dy over dt equals 2t. Either way, you have to solve for dy, so you'd multiply the dt to the right. Okay, so let's go ahead and find our line integral. So we're going to have a line integral from 1 to 3 of, let's see, it's xy. So x is t, y is t squared. So that's just going to give us t cubed plus the natural log of x, but that x again is t, so it's natural log of t. And then dy, which is 2t dt. So we're going to have to distribute. So distributing the 2t, we're going to get 2t to the 4th, and then 2t plus the natural log of t dt. So the antiderivative of the 2t to the 4th part will not be a problem. Taking the antiderivative of 2t natural log of t is not so easy. U substitution doesn't work there, so it looks like probably integration by parts is going to be the way to go. So let's go ahead and separate our integrals. We'll do the integral from 1 to 3 of 2t to the 4th plus the integral from 1 to 3 of 2t natural log of t dt. So we'll do parts. All right, so if you remember integration by parts, u is going to equal, let's see, it's LIPET, so logs are first, so u has to equal the natural log of t. Then dv is going to equal everything that's left, which is 2t dt. We need du, which is 1 over t dt. And we need v, the antiderivative, so the antiderivative of 2t is going to be t squared. So for our integration by parts, it's uv, so t squared ln of t, minus the integral of v du, so t squared times 1 over t dt. Don't forget I've still got this other integral out here that we have to deal with. That one will be easy. Oops, forgot the dt part here. Easy to do. Forgot to distribute the dt. All right, so I think we're probably in a pretty good position now. So the antiderivative of 2t to the fourth is going to be 2/5. That is a 2. 2/5 t to the fifth from 1 to 3 plus. Now I've got t squared natural log of t. The integral part is t squared over t, which is just t. So if I take the antiderivative of that, it'll be minus 1/2 t squared. And we have to evaluate that also from 1 to 3. So we could drop the separate 1 to 3s and just do the whole thing, or whatever. It doesn't really make any difference. So I'm just going to evaluate the whole thing from 1 to 3 since, I don't know, to me it makes sense to do it that way. So if I plug the 3 in to the t to the fifth, let's see, 3 to the fifth. 3 to the fourth is 81. So times 3 more is 243. Times 2, geez, trying to do this in my head, 486, I believe, 486 over 5. Minus, plugging the 1 in, I get 2/5, so minus 2/5. I'm going to do it separately now that I'm thinking about it. All right, now we'll do the second one. So we're going to get, let's see, plugging a 3 in, we get 9 times the natural log of 3, whatever that is, minus 9/2, that's plugging the 3 in, minus, plugging the 1 in, I get 1 times the natural log of 1, natural log of 1 is 0, minus 1/2. What an ugly answer this is going to be. So 486 minus 2 for the fifth part is going to be 484. 484 over 5. Let's make that look like an actual 4 instead of a really funky looking S. Plus 9 natural log of 3. Not much we can do with that. And then we've got minus 9/2 minus a minus 1/2, so plus a 1/2. That's going to give us minus 8/2, which is minus 4. Wow. Okay. We could certainly combine the 4 and the 484 over 5, but I am not worried about doing that. I think it would be 464 over 5, because 4 in terms of 5 would be 20 over 5, so you could do that. All right, but there is your line integral. All right, and here we have another one that has these dx and dy's as opposed to ds's. Again, this will be something that we talk about in part B of the section. All right, C is going to consist, oh, nice, line segments. Those are always the easiest thing to do. The line segment from 0, 0 to 2, 0, and from 2, 0 to 3, 2. So we'll call this one C1, and we'll call this one C2. So we're still going to have to separate this and do two different ones. Line segments are the easiest ones to do, though. So for C1, because it's linear, let's see, how does x change? X goes from 0 to 2. So it starts at 0 and increases by 2. So x is 2t. The y one is always 0. Doesn't change. Let's look at line segment number 2. So let's see, x starts at 2 and increases by 1. So it'll be 2 plus t. Oops, that's supposed to be x equals that. And then y goes from 0 to 2. So it starts at 0 but increases by 2. So y is 2t. Let's see, what are we going to need? For C1, we're going to need dx. For C2, we would need dy. So let's see what we're going to get. For C1, oops, let's do it in green. For C1, remember that because these are both lines, I'll write this in red in between, both of the t values go from 0 to 1. That will always be the case for line segments. So our integral will go from 0 to 1. Let's see, we need x, y, dx. Well, x times y is going to be 2t times 0. So wonderful. That's 0. I don't really care what dx is. Doesn't matter. Because it's 0 times something. It's gone. Plus x minus y, which is 2t minus 0, times dy. But dy is still 0 since y was 0 in the first place. So here we get 2t times 0. Awesome. That's 0. Very cool. Easy to do. Let's look at C2. Don't think this will work out quite as nice. C2. So we're going to need, let's see, xy, which is going to be 2 plus t times 2t. So integral 0 to 1 of 2 plus t times 2t dx. From the C2 part, the derivative of the x part is 1 dt. So we'll get dt there. Plus x minus y is 2 plus t minus 2t dy. Derivative of y here is going to be 2 dt. So 2 dt. So I technically have a dt in common. I can pull that one all the way out to the right-hand side. Go ahead and simplify everything on the inside here. So we're going to get, let's see, distributing, we're going to get 4t plus 2t squared plus, let's see, that'll be 2 plus t right here minus 2t is going to be 2 minus t. But you got to distribute the 2 in here. So that'll give me 2 minus t for that part. Distributing the 2 is going to give us 4 minus 2t dt. Okay, so let's go ahead and simplify even more. So I'm going to have 2t squared. I've got 4t minus 2t, which is plus 2t, plus 4 dt. So now let's go ahead and take antiderivative. So we're going to get 2/3 t cubed plus t squared plus 4t from 0 to 1. Good thing is plugging the 0 in there wipes everything out. So plugging in the 1 is all I have to worry about. We get 2/3 plus 1 plus 4, which is going to be 5 plus 2/3. 5 in terms of thirds is 15/3, so we're going to get 17/3. So remember that the entire line integral over C is going to be the line integral over C1 plus the line integral over C2. That's really poor notation, but just want to make sure you know you're actually adding these two things up. Granted, the first one was 0, so that makes this 17/3 because it would have been 0 plus 17/3. So there's your line integral for that one. All right, 2 more examples. Example 6, we want to do the line integral of x plus yz dx plus 2x dy plus xyz dz. Where C consists of line segments. Again, line segments are awesome. So we've got 2 different line segments. So again, we're going to call this one C1. And can't do it really great here, but we're going to call that one C2. So let's go with C1. Let's parameterize C1. Now we do have x, y, and z to deal with here. So let's see. X is going to start at 1 and increase by 1, so it'll be 1 plus t. Y is going to start at 0 and increase by 3, so that'll be 3t. And z looks like it is always 1, goes from 1 to 1. Okay, let's parameterize C2 while we're at it. So x is going to start at 2, and it's always going to be 2, so it doesn't change. Y is going to start at 3 and increase by 2 to get to 5. And z is going to start at 1 and increase by 1 to get to 2. And because it is line segments, t goes from 0 to 1. All right, let's start plugging stuff in here. For C1, probably have to scroll back and forth a little bit here. C1. So we're going to do the line integral from 0 to 1. X plus yz. We're dealing with the green now. So x is 1 plus t plus yz is going to be y times z is 3t. Dx is going to be 1 dt, so that's just dt, plus 2x, so that's going to be 2 times 1 plus t times dy. dy here is 3 dt, so times 3 dt. And then xyz is going to be 1 plus t times 3t times 1 times dz, but dz is 0. So that whole part's going to go away. All right. Let's do what we can to combine some terms here. So this is going to be 1 plus 4t dt. I'll pull the dt out to the right again. This one right here, I'm going to distribute that 6 through, so we're going to get 6 plus 6t. 6 plus 6t. All of that dt. Combining some terms, we'll get an integral from 0 to 1 of 7 plus 10t dt. All right, so it looks like we're going to get 7t plus 5t squared evaluated from 0 to 1, which is just going to give us 7 plus 5, which is 12, because the 0, again, is going to make everything go away. So that is the line integral over C1. Now let's do C2. This is where I'll have to scroll back and forth a little bit, I think. So C2 should be an integral from 0 to 1. 0 to 1. Okay, so the first one is going to be x plus yz dx. The nice thing about that one is dx is 0. So that whole first part is 0 dt plus. The second one is 2x, which is 2 times 2 dy. dy is 2 dt. So we're going to get 2 times 2 for the 2 times x part times another 2, which is really just going to give us 8 dt. And then for the third part, it's xyz times dz. dz is 1 dt. So I do have to multiply the 2 times the 3 plus 2t times the 1 plus t. So here we're going to have 2, 3 plus 2t, 1 plus t dt. So let's see what we get when we start combining stuff here. So we're still going to have that 8. I'm going to have to FOIL this. That's going to give me 2 times, let's see, that'll be 3 plus 2t, and 3t is 5t. Last is going to be 2t squared dt. So let's see. I'm going to distribute the 2 and I'm going to combine like terms. So if I distribute the 2, we're going to get a 6 plus an 8, which is 14, plus a 10t, plus a 4t squared dt from 0 to 1. So the antiderivative will give us 14t plus 5t squared plus 4/3 t cubed from 0 to 1. So again, the 0 part won't make any difference. So that'll be 14 plus 5 plus 4/3, which is going to be 19 plus 4/3. Let's see, 19 in terms of thirds is going to be 57 thirds. So 57 and 4 is 61 thirds. So that's C2. So the entire line integral over C of our function, I'm just going to call it f for lack of writing it in a better way, is going to be 61 thirds plus 12. 12 in terms of thirds is 36, so we should get 97 thirds. Again, not exactly short, but not extremely difficult to do, especially if they are linear. All right, one more. I know we're at 20 minutes, but we're going to finish this one off. We're going to push through it. All right, so a little bit of a word problem here. The base of a circular fence with a radius of 10 meters is given by x equals 10 cosine t, y equals 10 sine t. So already parameterized, that's nice. The height of the fence at position xy is given by the function h of xy equals 4 plus 0.01 x squared minus y squared. So the height varies from 3 to 5 meters. It's telling us that. Suppose that it takes 1 liter of paint, which covers 100 meters squared, I guess, of space. Sketch the fence and determine how much paint you will need to paint both sides of the fence. Okay, so basically this fence is acting as our ribbon. So the first thing is x equals 10 cosine t, y equals 10 sine t. Hopefully you remember is the parametric form of a circle with a radius of 10. So because of space here, I'm just going to say that this thing right here is our circle with a radius of 10. Okay, that's the projection down into the xy plane. It says that it varies between 3 and 5 meters. So I'm assuming, I shouldn't assume, oh, we could use the height function to figure it out. Okay. So when x and y are zeros, okay, so when x is 0, y would have to be y would have to be 10. Okay. So that would be 4 minus, let's see, 10 squared is 100. 100 times 0.01 is 1. So 4 minus 3. Okay. So that means, I know I'm doing a lot of stuff in my head, that this right here has the height of 3. That's a height of 3. But that also means that the other side over here is going to have a height of 3. That means that the ones that follow the x-axis must have the height of 5, because then you're adding the extra 1 to the 4. So over here, that's got a height of 5, so these are going to be taller. So it looks like the fence kind of winds itself like in some kind of a, comes down, goes back up, and it comes down, it goes back up. This is a weird looking fence, at least the way I'm drawing it. It's supposed to be more circular in nature. Again, I'm not very good at drawing it, but here is your fence. You can kind of see it, hopefully, something like that. There's our sketch. Not the best. I don't know. I kind of think of it as looking almost like one of those trampolines or something like that. I don't know. Doesn't matter. That's the best I'm going to do. And it just says sketch. Doesn't have to be a work of art. So we want to know how much paint, I guess, we're going to have to use. So how much surface area there is to do both sides of the fence. Well, the line integral only gives you the area of one side. So basically, you'd have to double the answer here. So what do we know? We know it's already parameterized because they've given us that. We know it's circular in nature, and the base, or the blue part, the curve, goes all the way from 0 to 2 pi. So I do know that my line integral is going to go from 0 to 2 pi. Okay, the function that we're parameterizing is this height. So that's going to be 4 plus 0.01 times x squared minus y squared. Boy, I wish that was plus y squared. It would be so much easier. It's not. So x squared is going to be 10 cosine squared t minus, I'm not 10, this would be 100 because it's squared, minus 100 sine squared t. And then we have to do ds, because this one does not have a dx or dy or anything like that. This is ds. This is over the arc length. So the derivative of the x part is negative 10 cosine t squared plus the derivative of the y part, oops, that should be negative 10 sine t, sorry. And then the y part is going to be 10 cosine t squared dt out there on the right. Okay, let's see what we get. I definitely want to simplify this before I try and integrate. So I got 4 plus, I can factor the 100 out of here and multiply it by the 0.01 on the outside, and that's just going to give me cosine squared of t minus sine squared of t, because the 100 times the 0.01 is 1. This piece is going to give us, let's see, if we square everything, we get 100 sine squared t plus 100 cosine squared t. Wonderful. Factoring out the 100, you're left with a sine squared plus cosine squared, which is 1. You can then take the square root of 100, which is 10. And really, there should be a bracket here, because that 10 that we pull out has to get distributed to everything, or I can just pull it all the way out to the front. So now I have to take the antiderivative of 4 plus. Now, there is an identity, which is really nice here. And if you don't remember this one, I'm going to give it to you. Cosine squared minus sine squared is the same thing as cosine of a double angle. So that's the same thing as cosine of 2t, which will make this so much easier to do. So now we can go ahead to find the line integral, take the antiderivatives. So we're going to have an don't want to write 0 to 2 pi anymore. So we're going to have 4t. So that's going to be plus, excuse me, antiderivative of cosine is sine. Don't forget the extra 1/2 from the front. And we will evaluate that from 0 to 2 pi. So we get 10 times. Plugging in 2 pi, we get 8 pi plus sine of 4 pi is the same thing as sine of 0, so that's 0. That's gone. Minus. Plugging in 0 for both of the t's gives us 0 plus 0. So really what I get is 8 pi times 10, or 80 pi units. That's the surface area of the fence. That's one side of the fence. This represents one side of the fence. So then obviously what I'm going to have for the total surface area of this thing is a 160 pi surface area for both sides. But they have given me some kind of awful conversion. So let's see. This is in, I guess, meters. So 160 pi meters squared divided by 100 meters cubed per liter is going to be approximately, actually it's not approximate, I think it works out to be right, 5.0625 liters of paint. So there we go. That's how much paint we'd need to do this one. All right, plenty long enough, but I did keep it to under 30 minutes, which is good. So these problems are not short. Again, as you can completely see, take your time on them. They're not difficult, just do them right.